Continuing section 8.1 with one final example about Burger King's drive-thru. So it says, suppose that cars arrive at Burger King's drive-thru at a rate of 20 cars every hour between noon and 1 p.m. A random sample of 40 one-hour time periods between noon and 1 is selected, and it has a mean of 22.1 cars arriving. So why is the sampling distribution of X bar approximately normal? So again, you're either looking for the words normally distributed, or you're looking for a sample size bigger than 30. So the answer for that is because n is greater than or equal to 30, because the sample size was 40. What is the mean and the standard deviation of the sampling distribution, assuming that the true mean is 20, and there should be, it won't print, I put it in there, but it won't print. There should be a standard deviation right there, sigma. Before that equal sign, I put it in there, but it doesn't want to print. So what is the mean and the standard deviation, assuming that the true mean is 20 and the true standard deviation is the square root of 20? So the mean of all the samples will still be around 20, and the standard deviation of the samples will be the original standard deviation of the population divided by the square root of the sample size, which is 40. So let's see, the square root of 20 divided by the square root of 40. When you do this, you do need to close those parentheses between. On the newer calculator, square root of 20, you'll do the over arrow. You can't see that. So on the newer calculators, push over to make the square root stop, divided by the square root of 40, and then push over to make the square root stop. So you should get, 0.7071. So when you have an ugly decimal for the standard deviation, you have to give it at least 4 decimal places, 5 to be really on the safe side, but at least 4, so that you don't over round your answer. So 0.7071 is what we're going to use for the standard deviation. If it comes out nice, that's one thing, but if not, you want to use at least 4 decimal places, or you can type this whole thing in every time. So that's up to you. As long as you have 4 decimal places, you should be good. So part C says, what is the probability that a simple random sample of size 40, 1-hour time periods, results in a mean of at least 22.1 cars? So normal CDF. At least 22.1 would be 22.1 to infinity. Mean of 20, and we're going to use that adjusted standard deviation to do our calculation. So let's see. Normal CDF, 22.1, infinity, 20, and then 0.7071, or you can type, you can't see, you can type that in again as well, either way, and then enter. You get 0.0015. It says, is this result unusual? The answer to that is yes. And then it says, what might we conclude? So there's a couple things we could conclude. It could be that it's just a busy time of year, and so we just have a larger number of cars coming because those 41-hour time periods was just a busy time of year. Another thing we might conclude is that 20 might not be accurate anymore. That might be an old estimate that needs to be updated. So we're going to talk a little bit more about that in Chapter 10, like what's going on if a result is unusual. But again, that sometimes means that whatever you're looking at is a rare case. Something weird was happening, or it might mean that the original mean that you thought was true is no longer true. So a couple different ways to interpret an unusual result. Again, we'll talk more about that when we get to Chapter 10. Alright, the second half of Chapter 8 is a new type of variable that we haven't studied before, and it is called a sample proportion. Now, we've heard the word proportion before, but we haven't used it in this way. So this is a new type of variable that we haven't seen before. So a proportion is the same thing as a relative frequency. That's still true. So you take the desired outcome and divide by the total number in the sample, and the notation is called p hat. So p with a little hat is x over n. And it's very important to remember that it's always a decimal. And it's going to be between 0 and 1. So all proportions are decimals between 0 and 1. So it's not difficult, but students really have to pay attention to what kind of numbers you're putting in the calculator. If it is a proportion, you have to put in a decimal between 0 and 1. So that is on your formula sheet as well. This is something that I think students just go too fast and they don't pay attention to what kind of numbers they're putting into the calculator. So it's very important to remember that a sample proportion is a ratio, and it's always going to end up as a decimal. So that's something that we just tend to overlook. So we're still going to look at shape, center, and spread. A little bit different way here because we're dealing with a ratio or a percentage instead of just a mean. So the shape of the sample proportion distribution is approximately normal, which is what we want, if these two conditions are met. The first condition we saw back in chapter 6, I believe, n times p times 1 minus p needs to be at least 10. So we've seen that before. That still has to be true. The second condition we don't see as much. I'll show you a couple times, but it's not as common. And that's that the sample size needs to be less than or equal to 5% of the population size. So remember, lowercase n is sample size, capital N is population size. That's a condition we haven't looked at before, and we'll check it a couple times. Generally, this is assumed to be true. So generally, we don't have to do anything. I'll show you a couple instances where we do, but it's generally assumed to be true. Now, when you're doing your own data and research, if you go on to do that after this course, you'll have to actually check that condition. For our class, we're just going to kind of assume that it's true. The center for a sample proportion is just like the center for a sample mean. So the average of all the sample proportions is going to equal just p, which is what we call the true proportion or the population proportion. So when you see the word true, that also means population. So the average of all the sample proportions will be the true proportion, which will be given to you in the problem. The spread of a sample proportion distribution is a different calculation. So the standard deviation for all the sample proportions is the square root of p times 1 minus p over n. And I don't think we've seen that calculation before. So it's a little different than it is with means. So you'll see those two things here on your formula sheet. The mean is equal to the true proportion, and the standard deviation is this calculation. And that's new to us. All right. So now we have two different types of variables, and throughout this unit, we're going to see both types of variables in Chapter 8, Chapter 9, and Chapter 10. So we have means or averages. This was from Section 8.1. And then we have proportions, which is what we're just learning about now. And there's a few key differences between the two to help you decipher what type of problem you're looking at. So this chart that I made for you is not in the textbook, but I think it's very helpful to refer back to as you get into Chapter 9 and Chapter 10. So you might want to just kind of highlight it and know that this is going to be true throughout this entire unit of inference. We're going to have two types of variables throughout the rest of the course. So you can refer back to this page as often as you need. Alright, so the first thing is the notation. When we have means and averages, we're going to see mu, and we're going to see x bar, and we're going to see sigma. So you're going to have means, you're going to have standard deviations, you're going to have sample means. When we have a proportion, which is a percentage or a ratio, we're going to have p, the true proportion, and we're going to have p hat, which again is x over n. We're not going to be given a standard deviation, and I'll talk about that more in a minute, to make this decision. So if you're given a standard deviation, you're probably working with means. If you're not given a standard deviation, you're probably working with proportions. So to check the shape, to make sure that it's normally distributed, for means, it might be stated in the problem. That's the easiest way. Or the sample size is at least 30. That's an easy check. Or the third way we could check is the normal probability plot. Now we don't have to do that very often, but that was back from section 7.3. Sometimes we actually have to go look at the plot if our sample size is not big enough to make sure that it makes a straight line. So most of the time it's stated in the problem or the sample size is at least 30, but I do think I have one example where you have to check the normal probability plot. For proportions, it's never going to be stated in the problem. So these are all or. But there's two conditions you have to check for proportions. You have to make sure n times p times 1 minus p is greater than or equal to 10. And the second condition, the sample size has to be less than 5% of the population size. The first condition is the one you're going to check the most often. The second condition, like I said, we generally assume it to be true, but every now and then you will have to check it. The centers are the same, so the center of all the sample averages is the true average. The center of all the sample proportions is the true proportion. That part's easy. And finally, standard deviations. The standard deviation for all the sample means is the true standard deviation divided by the square root of the sample size. The standard deviation for proportions is the square root of p times 1 minus p over n. So that's a little bit more involved calculation. So you have to read the scenario for each problem to determine if it's referring to means or proportions, and then work the problem appropriately based on which one it is. The biggest hint is that if the standard deviation is given, you're working with means. So your biggest giveaway is the standard deviation. If the standard deviation is given, you're working with these conditions. If the standard deviation is not given, you're given a percentage or a ratio, you're working with these conditions where you have to come up with the standard deviation all on your own. Alright, so we're going to look at some examples of proportions. Section 8.1 was all the means. Now we're going to look at some examples with proportions. So the first example, based on a Gallup poll, 76% of Americans believe that the state of moral values in the United States is getting worse. Suppose we took a random sample of 60 people. Describe the sampling distribution of the proportion of the sample that believes the state of moral values in the U.S. is getting worse. So the first thing we want to do is to check to see if the shape is approximately normal. The first condition is the sample size less than 5% of the population size. Notice in the problem they do not give us the population of the U.S., and I personally do not know that off the top of my head. I know it's in the millions, maybe it's in the billions, but I don't know what the exact number is. So for this condition, we're going to assume it to be true. Now in this example, we'll actually work it out, but for this one, we're just going to assume that that condition is true. The second condition we're actually going to check. Notice they gave us a percentage in the problem and they did not give us a standard deviation. So that is our proportion as a decimal, 0.76. And our n, our sample size, is 60. So we want to make sure that 60 times 0.76 times 1 minus 0.76 is at least 10. So let's crunch those numbers. 60 times 0.76 times 1 minus 0.76 And let's make sure it's 10.944, and as long as it's at least 10, we can say that that condition has been met. So we're assuming the first condition to be true. We've checked the second condition. Therefore, the shape is approximately normal. The next check is the center. The center is easy. So the mean of all the sample proportions will be 0.76, the true proportion. And finally, the spread. The standard deviation of all the sample proportions will be the square root, 0.76, times 1 minus 0.76, divided by our sample size of 60. Now practice putting this in the calculator, because it is a little tricky when we get to square roots. The calculator does follow the order of operations. You just want to make sure that all your calculations are under the square root bar. And with the newer calculators, again, you just have to watch to make sure 0.76, 1 minus 0.76, that square root bar should be following you across, divided by 60. So you want to make sure it follows you all the way across till the end of the problem. So you should get 0.0551. So when we're running problems with this, we're still going to use normal CDF, but this is going to be our center, our mean, and then we're always going to use this adjusted standard deviation. So same idea as chapter 7, except our mean, instead of being an integer now, is a decimal, and the standard deviation is going to be a pretty small decimal. Alright, so let's look at the next example. I just pulled this out of the textbook. It says just to describe the sampling distribution. It says assume that the size of the population is 25,000. So now we have a number to work with for capital N. So to check the shape, we're going to do N times P times 1 minus P. Make sure it's at least 10. So 500 times 0.4 times 1 minus 0.4. Let's type that in. I got 120, which is at least 10. Now the second condition I can actually check, and I'm sorry I didn't quite give you enough space here. I'm going to do the second shape check down here, and that's to make sure that the sample size is less than 5% of the population size. So our sample size is 500. I want to make sure that that's less than 5% of that population size, 25,000. So I'm going to do 25,000 times 0.05. Whoops. Let's see if I can type correctly today. So 25,000 times 0.05 should give you 1,250. You want to make sure that 500 is less than 1,250, which it is. If those two conditions are met, we can say the shape is approximately normal, which is what we want to be able to answer questions about these problems. The next check is the center. Center never requires any work. The mean of all the sample proportions will be the true proportion, 0.4. And finally the spread. The spread will be the square root, so that's the standard deviation of all the sample proportions, which is the square root of 0.4 times 1 minus 0.4 over 500. So let's work that out and get our decimal. 0.4 times 1 minus 0.4 divided by 500, all under the same square root. You should get 0.0219. And again, you want at least 4 decimal places. Sometimes on the homework they want 5 or 6, just to make sure you've got all your values and you're not rounding too much. So if you want to, pause the video, try part B on your own, and then check and see how you did. So we're going to do the same thing for part B. Let's check the shape. So 300 times 0.7 times 1 minus 0.7. We need to make sure that's at least 10. I got 63, which is at least 10. Let me just make sure I missed a parenthesis there. Let me double check. Yep. So as long as that's at least 10, you're good. And then you want to make sure that 300 is less than or equal to 0.05 times that 25,000. Remember that we've already calculated that, which was 1250. So 300 is, 300 is less than or equal to that 1250. For the center, you don't have to do any work. The mean of all the proportions will be that true proportion, 0.7. And finally, the spread will be the square root of all the sample proportion. Sorry, the standard deviation of all the sample proportions is 0.7 times 1 minus 0.7 over 300, and all of that under the square root. So square root 0.7 times 1 minus 0.7 divided by 300. You should get 0.0265 if you round to 4 decimal places. I'm going to stop there so the video does not cut me off, and then we'll get into the last few examples.